Hello again. This chapter is on hypothesis testing. So we have previously looked at estimation, which was dealing with trying to get or obtain values of population parameters from samples. And here we are going to go further and make some decisions or investigations about the value of population parameters based on samples. So there are two particular population parameters we'll look at: population mean and population proportion. And we'll start off by looking at some basic ideas and then move on to the types of errors that can be, in this case, that can happen or occur in hypothesis testing. We'll take a look at the distinction between one-tailed and two-tailed tests, and then move on from there to proportions. So, in the previous chapter, we looked at estimation, which is about trying to obtain information on the values of parameters based on samples. Here in hypothesis testing, we're going to try and evaluate the evidence for the values of parameters from either previously held values or some claims or whatever else. And this evaluation will be based on the data from the sample. So here, as I said, we're looking at population mean and population proportion only. The methods are similar, and we'll develop them with an example. So here's the example that we'll be looking at. The claim here is by the manufacturer that the mean weight of this box of detergents is at least 3.25 kilograms. And so a sample of 64 boxes gave us a mean that's slightly lower than that, 3.238, and a sample standard deviation of 0.117. So what do we conclude about the manufacturer's claim? Is the mean actually less than 3.25, or is the claim correct? So here the model of interest is yi, the observations, are simply a fixed mean plus some error term or some random variation. So if I think in terms of a normal distribution, for example, there's the mean mu, and I'm saying that the boxes have average weight mu, but every particular box I pick won't be exactly the same as mu. There's some random variation around the values. Now, if the variation is not too much and the average value is still close to mu, I mightn't have much to worry about. But in this case, is this close enough is the question. So how do we decide that? The first is we state hypotheses. So the null hypothesis is the hypothesis of no change. In other words, we believe what has been told to us or from past data. We take the value as being the same as that. This is the hypothesis of no change. The alternative is the expected change or the values that will cause us concern. So in the context of this problem here, H naught is going to be simply to believe the claim of the manufacturer. So it's going to be mu is bigger than or equal to. Mu is bigger than or equal to, the claim was is big, at least 3.25. So this means believe the claim. There's no evidence, there's no reason to go otherwise. We can't start by disbelieving the claim. So the idea with hypothesis test is innocent until proven guilty. And H1 is the values that give us problems are if the mean is less than 3.25. Now here, we would often just simply write mu equals 3.25 because, in fact, as you might have seen in the early examples we played with in hypothesis testing, excuse me, the equal value is what is being used in the end. So often you'll find we'll write simply mu equals 3.25. However, the form in the square brackets there may be more indicative and more better guidance, because that probably guides you with what H1 should be. It's just the opposite of what H naught is. So that's to believe the claim, and these are the values of H1 that give us problems. So the next is to select a test statistic and find its distribution. So here, of course, we'll be using the sample mean, but we'll standardize this first. So it's x bar minus mu on S on root n. And we know from our sampling ideas that this is a Tn minus 1 distribution. And here, because actually I know the value of n, that is 64, I can actually put the value in there, and I can then change this to reflect that. That's T63. So this is what I've got here. The next is to compute the value of the test statistic, observed value from the data, assuming H naught is true. So in this case, my observed value, T observed, or Bs, of the test statistic from the data, my actual value from the sample was 3.238. My mean or equals value is 3.25. My standard deviation, excuse me, my sample standard deviation is 0.117, and it's all over root of 64. So if I compute all that, what I'll get there is my value comes to negative 0.82. So note this value here is the value from my null hypothesis. And as it says, it's the equal value from the null hypothesis. So that's the first few steps. Next is to find the p-value for the test statistic. And so the p-value is simply given as the probability that t is, and the value I had was from the data was negative 0.82. Extreme values are always away from the middle. So the middle here is 0, extreme is negative 0.82, and so that's where my p-value lies. And also, if you look at my statement for H1, H1 said mu is less than 3.25. So that less than also occurs here. These have to be consistent. They will be the same. That's my p-value. Now, the distribution this comes from is going to be t, the random variable t is a t63 distribution. So the p-value I can find from packages R or some other similar package. In this case, if you do the computations, this comes to 0.2077. Now, the way this works, as we've seen earlier in our hypothesis testing examples, is that we need to decide how to make a decision on this. How do we decide if we reject the null hypothesis or don't reject the null hypothesis? And that is all about the p-value. If the p-value is small, then the data and the null hypothesis are inconsistent and we reject the null hypothesis. If the p-value is large, there's no reason to doubt H0. In other words, the data is consistent with the null hypothesis. So, what's small and large, as we saw earlier, this is going to be decided by a significance level that's preset. So for one tail test, essentially this is less than or bigger than, p-value is less than alpha, reject H0, bigger than alpha, fail to reject H0. We usually take alpha to be 0.025, and we'll see why this is the case. Most people we might find take 5%, we'll take 0.025 here. So our p-value here is 0.2077, and that's quite large compared to 0.025. So there is insufficient evidence to reject H0. Now in this case, the idea is that the actual mean we saw observed is less than 3.25. But that is not sufficient evidence in terms of p-values. And usually we'll quote the level of significance. So that's our statement of the hypothesis test. Then the conclusion must be stated in terms of the question. And the important thing here is the manufacturer's claim correct? So we conclude based on this analysis no reason or no evidence. All right. In other words, there's nothing here that suggests the mean actually is less than 3.25 kilograms. Now, the distribution that we used here, the Tn-1 distribution, that was what we obtained in our discussions on sampling idea. So that's where that comes from. As we said earlier, the hypothesis could easily be taken simply as mu equals 3.25 versus mu less than 3.25. But the equal sign always stays with the null hypothesis. So you'll never write this next statement. You'll never write the thing as mu bigger than 3.5 against mu less than equal to. That would be incorrect. The p-value is just the probability of extreme values with respect to h0. So what we're saying here is, what's the probability of observing data as extreme as we have observed, or more extreme, assuming that the null hypothesis is true. And so as I said, in every case, if I have h1 says mu less than some value mu naught, then the p-value is going to be in the left tail. Probability t is less than equal to t observed. And if my h1 is the other way, mu bigger than some value, then my p-value is going to be in the right tail. So p-value is probability of t being bigger than or equal to t observed. So that direction and that direction are the same. If you don't have that, then you should be a bit concerned. A sketch of this kind always works as to what extreme means here. As another example, we're looking here at a manufacturer who claims that the light bulbs they produce last more than 1,000 hours on average. So that's our mean. A sample of 100 light bulbs were tested. They gave a mean lifetime of 991 hours and a standard deviation of 87.2 hours. What should we conclude about the manufacturer's claim here? So here, first of all, we start off by defining ourselves a variable of interest. So let mu denote or equal the mean lifetime of the light bulbs. So then my hypotheses are going to be, well, it's just simply mu equals 1,000, and h1 is that it's not 1,000, it's less than that. So it does say last more than, so we could actually have written also mu as being bigger than equal to 1,000, and that's also going to be okay. Now, excuse me, in terms of the test I have here, this is a lower tail test because I'm looking for the p-value in the lower tail. Or sometimes called the left-sided test. And so this other one is going to be a right-sided test. So in this example, what we have is a left-sided test. Our test statistic, as before, will be the t. So that's t equals x bar minus mu over s on root. And I've had, excuse me, I've got 100 light bulbs over here. So that's going to be T99. Next part is to calculate the observed value of this, assuming H0 is true. So T observed is going to be, my X bar was 991 hours. The mu is 1,000 hours, and that's the H0 value, and that's what I'll be using. Then is this S on root n idea. The S is 87.2, and root of n is root of 100, and that comes to negative 1.03. So, as it's a one-tailed or one-sided test, we'll take our significance level alpha to be 2.5%. And so what I need here now is a p-value. So the p-value here, in terms of, because this was a left-sided test, it's less than equal to my observed value, negative 1.03, where this t is a T99 distribution. And that probably, again, we'll use R for this, and we get 0.1535. So we can either use R to obtain this, or be given this. And so in this case, there is insufficient evidence to reject the null hypothesis again. So here we'll conclude and based on this data, based on this analysis, or data, they're both good enough in this case. We have no reason to doubt the manufacturer's claim, so there's no evidence against the manufacturer's claim. So that's basically hypothesis testing, and every test looks similar in that sense. Before we proceed, just one more idea. Instead of using a p-value, I can use what's called a critical region for hypothesis testing, and this is an idea you might see in some other places. To me, it's an old idea because this was when tables weren't available, when machines weren't available, and we used tables. Now we have machines we can use p-values. So let's take a look at the example again here. If I'm looking at the critical region idea, my alpha value was 0.025. So if this is my T99 distribution, then the probability here of 0.025 in the tail, I'm going to find the value, and that comes as negative 1.984, and I'm again use R for this. Now, my actual observed value was negative 1.03. So this region here that I've labeled here, essentially shaded, is my critical region. Or sometimes called the rejection region. This critical in the sense is defined by my alpha level. So obviously, if this value here that I've observed lies in the critical region, then my p-value will be less than 0.025. If it's not there, then you can see the probability I'm getting here, probability on the left of this, is bigger than 0.025. So the two ways of hypothesis testing are equivalent, exactly the same. So if T observed is in the critical region, then p-value is less than alpha. So rejects the null hypothesis. On the other hand, if the observed value of my test statistic is not in critical region, then clearly the p-value is bigger than alpha. So here we'll fail to reject the null hypothesis. So these are equivalent, but the p-value does give us more evidence. It gives us a size, if you like, of how far away we are from the null hypothesis. In other words, how extreme is our observations. And that's a good place to stop. We'll take it from there in the next lecture.